Hello, and welcome to today's webinar, Thermal Management Solutions for Embedded Computing Systems. I'm Lisa Riga with TechBriefs Media Group, your moderator for this program. Our speakers are Kim Fixie and Jens Wyant with Advanced Cooling Technologies. Kim Fixie is the application engineer for the company's Defense, Aerospace, and Custom Products Group, where she diagnoses complex thermal challenges and then develops the appropriate thermal management solutions. Jens Wyant is manager of Defense and Aerospace Products and has contributed to thermal solutions for radar, power electronics, rotating equipment, and other high-power electronics, many of which include heat pipe embedded solutions. Today, Kim and Jens will provide insight on enhancing each level of a thermal resistant network by increasing thermal conductivity with passive thermal technologies. Heat pipes, vapor chambers, and enhanced thermal locks will be discussed, as well as best practices for designing the ultimate air or liquid-cooled heat sink. Our webinar will include an audience Q&A. Please send us your questions at any time by using the Ask a Question box on the screen. And now, please join me in welcoming Kim Fixie. Hi, Kim. Thanks for joining us today.
Thank you, Lisa. And thank you to everyone in attendance for this webinar. Today, we will be exploring thermal management solutions for embedded systems. I, along with Jens Wyant, are delighted to have you join. In this webinar, we will address typical thermal challenges that arise while designing embedded computing systems, use a case study to break down the thermal resistance network, and explore advanced cooling techniques to handle higher amounts of waste heat. An embedded system is one in which multiple smaller electronic components make up a larger function. These systems are typically arranged in a chassis with card slots for the mechanical assembly. The chassis can vary in its final size and dimensions, but often follows VIDA standards. VIDA is an organization of vendors that have a common market interest in real-time, modular embedded computing systems. For this webinar, we will focus on the cooling techniques for chassis that follow VIDA standards, which range in markets from medical imaging to space launch control, and follow the recommended standard VIDA 48 and VIDA 50. In embedded VME or VPX systems, the electronics boards attach directly to heat spreaders, which move the heat outward to the chassis. The edge of the chassis is attached using a card retainer, usually known as a wedge lock. This allows for easy assembly and quick servicing or replacing of the electronic boards. This connection transfers heat to the card guide or the chassis, which then dissipates the heat to either liquid or air to the environment. For liquid cooling systems, the liquid is typically located toward the base of the chassis, where air-cooled systems have fin stacks surrounding the hot areas of the chassis. The thermal load, ambient conditions, and available air or liquid flow will determine the dissipation method. Now I'll turn it back to Lisa for our first polling question.
Thanks, Kim. Our poll question is for everyone in the webinar audience. Let's bring it up on screen now. The question is, how often do you come across thermal challenges in your job function? Please select either often, sometimes, rarely, or never. Please submit your response now. Thank you. And now I'll hand the webinar back to Kim.
Thank you, Lisa. We will continue by diving into the thermal challenges in our case study. Our case study today presents a typical thermal challenge in an embedded system. Our embedded 6U card assembly holds two FPGAs that emit 50 watts of waste heat with a heat flux of 7.24 watts per centimeter squared. The card fits into a 1-inch slot and is liquid-cooled on the bottom of the chassis, with 40 degrees C inlet liquid temperature. The required case temperature for our FPGAs is only 50 degrees Celsius. leaving us a mere 10-degree delta with which to work. As we review our thermal results from our FPGA card, we can see a significant hotspot at T1. The first thermal challenge we can identify is once the heat enters the chassis. We will need to determine the best way to move the heat to the final heatsink and maximize the efficiency. The next critical point is the wedge lock. A standard wedge lock will have nearly 80% of the heat going directly through the card frame to the chassis. Only about 20% goes through the wedge lock. This creates a large temperature rise and a relatively short thermal path. The final area we will outline is the spreading along the card frame. If improved heat spreading is needed, copper is always an option. However, it adds weight to your system. As we continue to explore options that don't add weight, we'll look at heat pipes and high K plates. Now, to cool embedded systems, there are multiple interfaces in which thermal resistance stacks up. In breaking down an embedded system, we have 4 temperature zones and 4 resistance networks. The first temperature is that of either the liquid or air supplied to the system. We'll define it as T4. T4 is often fixed and determines what we can do with the rest of the system. R4, in our schematic, is the thermal resistance between the provided cooling and the chassis wall, where T3 is the temperature of the chassis wall itself. Our next zone looks at the thermal resistance network in parallel at the wedge lock. Wedge lock designs have multiple interfaces which create additional thermal resistance networks and really only support one thermal path to the chassis wall. Most embedded system designers consider it a bonus if any heat is transferred through the wedge lock itself. In our diagram, R2 and R3 display the parallel resistance network between the temperature of the chassis wall, T3, and the card edge, T2. The final resistance stackup and our last zone is between the card and the component where cooling is needed. T1 is the temperature seen by the component, or case temperature. Our goal in this case study is to lower T1 to 50 degrees C or below. To improve T1, we must reduce the resistance network and increase heat transfer capabilities on each of the 3 zones we just described. Now, high-level cooling, or the ultimate heatsink, is typically fixed and supplied by the full system the chassis supports. For an air transport rack, or ATR chassis, cooling is supplied via liquid, forced air, or natural convection air currents. The liquid cool systems allow the designer to determine the best plumbing to reduce the resistance stackup within the chassis, or R4. Natural convection and forced air both rely on an effective surface area, or fin design, to reduce the thermal resistance network to the chassis wall. Aluminum, with thermal conductivity of 167 watts per meter Kelvin, is commonly used due to its weight and strength benefits. However, with the low thermal conductivity, hotspots may occur, reducing the effectiveness of the surface area, or fin design. As we move on to the resistance network of the wedge lock, networks 2 and 3, we can find it as a source of pain for most chassis designers. The wedge lock system was designed as a ruggedized mechanical lock. Its secondary purpose is as a thermal heat transport system. Since it was not designed to optimize the heat transfer capabilities, typical wedge locks only offer one thermal path between the card and the wedge lock, and between the wedge lock and the chassis. This creates a thermal bottleneck and a temperature difference between the chassis wall and the card edge, or T2 and T3 in our schematic. A new wedge lock design that is optimized for thermal transport, while still meeting the VITA requirements for ruggedized mechanical hold, VITA 48.2, has been developed and will be discussed later on in this webinar. The final resistance stack-up is between the card edge and the case temperature. This can vary greatly depending on the board design and location of the hot components. For our case study, the high-power, high-waste heat components are located in the center of the card. This means heat has to transfer from the center of the card to the card edges, which means a greater thermal resistance than if the FPGAs were located near the card edge. To decrease the thermal resistance of the card or increase the thermal conductivity, heat pipes, high K plates, or vapor chambers can be used. Once again, we'll go to Lisa for our second polling question.
Thanks, Kim. This next polling question is about cooling. Let's bring it up on screen now. The question is, do you experience difficulties in keeping your critical components cool? Please select either yes, occasionally, no, or it does not apply to my job function. Please submit your response now. Thank you. And now Kim will continue with her presentation.
Thank you, Lisa. Now we'll explore the technical side of advanced thermal management methods. Starting with a heat pipe. A heat pipe is a closed, passive, two-phase heat transfer device that utilizes the latent heat of vaporization to transport heat. It consists of an envelope material, wick structure, and working fluid. At the hotspot, or evaporator, the working fluid vaporizes, creating a slight pressure difference, which causes the vapor to flow to the cooler end. At the cool end, the vapor will condense and return to the evaporator via capillary force or gravity. When designing a heat pipe into your system, it's important to identify several factors: power, heat sink and source parameters, and temperature range. These factors determine the required size and type of heat pipe selected. Since a heat pipe transfers heat via the vaporized working fluid through the center of the pipe, the amount of power transferred is affected by the vapor space available, which means a heat pipe can be built very small. However, it will have a limited amount of power in which it can transfer. Because the heat pipe is in a vacuum and is completely sealed, it operates along the saturation curve of the working fluid. Once the temperature range is identified, a working fluid will be selected. The envelope material is selected to be compatible with the working fluid at the high end of the temperature range. For an embedded system, the average working temperature is from -40 degrees Celsius to 125 degrees Celsius, with a typical max case temperature of 85 degrees Celsius. Therefore, the working fluid is typically water with a copper envelope material and wick structure. The next advanced thermal design is a high K plate. When hot components are spread in multiple locations and maintaining isothermality is a concern, one can use a high thermal conductivity plate, or high K plate. A high K plate is one in which heat pipes are directly embedded into a heat spreader, effectively raising the thermal conductivity of the plate. The measured thermal conductivity will vary by design, but will typically fall between 500 to 1200 watts per meter Kelvin, and can range in thickness to the thinnest being 1.8 millimeters, or 0.072 inches. The image displayed on the slide represents the thermal signature before and after heat pipes were embedded, creating the high K plate. Prior to the heat pipes being embedded, the electronic components were reaching 90 degrees Celsius, when their rating was 85 degrees Celsius. Since this plate was located in a finalized chassis design, the only thermal improvement possible was to the plate itself. The cooling rails, in which the plate were contacting, were supplied by a liquid at 40 degrees Celsius, much like our case study. Once the heat pipes were embedded, the component temperature dropped 25 degrees C. The high K plate reduced the thermal resistance between the plate edge and the hot components and maximized the effectiveness of the cold rails. When heat fluxes are extreme and the heat spreading requirements are demanding, vapor chambers offer a plausible solution. A vapor chamber is a closed, planar, two-phased heat transfer device. Similar to a heat pipe, it consists of an envelope material, wick structure, and working fluid. It uses the latent heat of vaporization to remove heat from hot components and spread it across the surface. Vapor chambers offer the same spreading capabilities as high K plates, but offer it at a higher effective thermal conductivity, which in turn provides a higher degree of isothermality. It can also handle higher heat fluxes, averaging about 700 watts per centimeter squared. These devices are typically found in systems that do require that high performance that a high K plate cannot meet. The figure on your screen shows how heat moves through a vapor chamber and is able to spread in the planar direction. As heat enters the device, it vaporizes the working fluid, which then flows to the condenser end of the plate due to the pressure difference. At the cooler end, the vapor chamber condenses and the liquid flows back to the evaporator due to the capillary force from the wick. Now, it is sometimes confusing to determine when heat pipes, high K plates, and vapor chambers are best utilized. Here is a table that summarizes each technology, evaluating density, spreading, thermal conductivity, max heat flux, minimum thickness, max height, and relative cost versus your typical aluminum. Progression from top to bottom shows an increase in the thermal performance. The table may assist the design engineer when conducting a thermal trade study for their application. In the spreading column, it refers to the dimensions that the heat can be spread. Heat pipes, as we discussed, spread in a single dimension, while aluminum, copper, and vapor chambers spread in the two-dimensional, or planar, directions. High K plates are the hybrid between the two, with the heat pipe component in the one direction and aluminum plate in the two direction. The ICE-Lok, or isothermal card edge, is the thermally enhanced wedge lock we discussed earlier in this webinar. This wedge lock utilizes both vertical and horizontal expansion to contact the chassis, which maximizes the surface area and reduces the thermal resistance. It consists of a spiral design that pushes the edge of the wedge lock to be in contact with the three surfaces. Where current wedge lock designs only expand in one direction and have a high thermal resistance, only 20% of the thermal load moves through the wedge lock due to that thermal resistance stack up in the current design. The enhanced design increases the surface area contact between the conduction card and the chassis and limits the thermal stack up, thereby improving the heat transfer with an overall lower thermal resistance. Initial tests of the ICE-Lok have indicated an increased heat transfer by 5 to 10 degrees Celsius. Now, once again, I'll turn it back to Lisa for our third and final polling question.
Thanks, Kim. Yes, let's bring up on screen now our last poll question, which is, have you ever integrated advanced thermal techniques into your program? Please select either yes, often, sometimes, rarely, or no. Please submit your response now. I want to thank everyone for participating in these audience polls today. And now I'll hand the webinar back to Kim.
Thank you, Lisa. Now we'll turn back to our case study and evaluate the thermal results. For our case study, we will now apply the advanced thermal techniques discussed today. Our goal again is to decrease T1 to 50 degrees Celsius to maintain the life of our FPGAs. To do this, we'll use a combination of heat pipes at the card frame, the ICE-Lok at the interface of the card edge and chassis wall, and a high K plate in the chassis. Our first enhancement will be applying the ICE-Lok. This is the easiest retrofit and can often provide you with 5 to 10 degrees C better heat transfer across that interface. Our thermal results show that T1 was reduced by 5 degrees Celsius due to that increased heat transfer capabilities of the ICE-Lok, where there is a delta T of 7 degrees Celsius across the wedge lock system. Our next enhancement will be applying a high K plate to the chassis wall. A high K plate is effective in both liquid and cooled systems, such as our case study, and air-cooled systems. In a liquid-cooled system, the high K plate will not only spread the heat along the chassis wall, but will transfer it directly to the cooled fluid. In an air-cooled system, the high K plate will spread hot spots evenly throughout the wall, which will increase the fin efficiency of the system. A high K plate can either be designed into the chassis wall or as a secondary bolt-on solution. This helps in retrofitting legacy chassis designs or designs in which power requirements have increased. By using the bolt-on high K solution, you create an additional thermal resistance network. However, due to the ability of the high K plate to achieve isothermality, you're able to achieve your desired isothermality and see negligible results from that additional resistance network. In our case study, applying a high K plate reduced our T1 by 15 degrees Celsius. The embedded heat pipes effectively spread the heat along the chassis wall and isothermalized the system. The final enhancement is to reduce T1, is to apply heat pipes to the card itself. The heat pipes are used to pull heat away from specific hotspots on the card and transfer it to the card edge. Spreading the heat along the card edge not only addresses the thermal resistance of the card edge to the component, but also reduces the effect of the thermal bottlenecking at that wedge lock. This is a thermal model. We can see the benefits of applying heat pipes compared to the baseline thermal model. The baseline model has a high conduction gradient and does not utilize the entire card edge, where the heat pipe solution increases the area and reduces the heat flux, while also significantly lowering the conduction resistance. In our case study, applying heat pipes to our advanced cooling techniques reduced T1 another 20 degrees Celsius. The overall reduction on T1 by applying the ICE-Lok, high K plate, and heat pipes was 40 degrees C, putting our case temperature on our FPGAs at 50 degrees Celsius. This case study shows how advanced thermal design can significantly improve the heat transfer capabilities of an embedded system and reduce the thermal resistance networks. Now, as demand for power increases and increased capabilities continue to rise, the need for proper thermal management does as well. Advanced cooling techniques such as heat pipes, high K plates, vapor chambers, or the ICE-Lok offer the ability to reduce key factors of thermal resistance networks in embedded computing systems. These advanced technologies can significantly improve the cooling capabilities in the card frame, the card chassis interface, and the chassis itself. I want to thank you for attending today's webinar on thermal management solutions for embedded computing systems. Now we will go back to Lisa for the question and answer portion.
Thanks, Kim. That was a great presentation. Lots of excellent technical information. Thank you. It's time now for our audience Q&A. Kim's colleague, Jens Wyant, the manager of the company's defense and aerospace products, will join us for this segment. Audience members may send questions by using the Ask a Question box on your screen. And our first question for Jens is, how do high K plates handle different heights and tolerances of electronics? Jens?
Excellent question. One of the benefits of a high K plate is that it can be machined the same way conventional aluminum conduction cards are. Typically, they are designed to contact the most thermally demanding components first, keeping that thermal interface to a minimum. The tolerance stack-up is then made with conformal gap pads for the remaining devices.
Thanks, Jens. Next question. Is the ICE-Lok available in any cross-section?
Currently, it's available in a 3/8 form factor. We're working on a 1/4-inch version right now.
Okay, very good. Next question. Someone wants to know, if I consider heat pipes because my heat spreader has too much conductive temperature rise, Would I need to add thickness to my heat spreader?
Not necessarily. In many cases, we're able to embed the heat pipes within the existing aluminum structure. Because the heat pipes are so flexible, we can flatten them and route them around existing features. Once the heat pipes are embedded, they can transport the majority of the heat, which means a lot of other areas can be actually reduced for weight reduction.
Thank you. And the next question is, how do you attach heat pipes to the heat spreaders? Jens?
In many cases, we prefer to solder the heat pipes. It's better thermally and mechanically. However, there are cases where a thermal epoxy is well suited. That depends on the heat flux, the allowable thermal gradient, and the coating requirements.
Okay, thank you. And with that, we're at the end of our webinar. If you sent a question that we did not have a chance to answer, the speakers will do their best to address it after the webinar. I want to thank Kim Fixie and Jens Wyant for being here today. I also want to thank our audience for joining us. A survey will pop up on everyone's screen in a few moments. Please tell us what you thought of our program by answering its 4 short questions. This webinar will be archived and available for viewing on the Tech Briefs website. An email will be sent to everyone who registered for the program as soon as the archive is ready. I'm Lisa Arrigo with Tech Briefs Media Group. Thanks for joining us.